Question number 4 from the book, 50 Challenging Problems in Probability. Trials until first success. On the average, how many times must a die be thrown until one gets a 6? Now this is a really simple problem, so I want to show you 2 ways that you could go about solving it. So the first way we could do it is using a geometric random variable. We can define x as the number of rolls until getting the first 6, and we know that each roll is independent and the success probability is 1/6. This is our exact setup of a geometric random variable. We know the expected value of a geometric random variable is 1/p. And from here, we know that we're expected 6 rolls until we get our first 6. Simple. The other way I want to show is something called using recursive probability. So we create a variable e, and that's going to be the expected number of rolls until the first 6. We can actually set up a recursion formula to demonstrate this process. So let's break this down. No matter what happens, we use 1 roll, and that's where we get this 1 from. Then, with 5/6 probability, we don't get our 6, and we're back where we started. And with 1/6 probability, so 1/6 at a time, we don't need any more rolls, so we multiply that by 0. Then we just use algebra to simplify and solve for e. You see you get the same answer using both strategies, so these are 2 valid ways you could solve problems like this. You could also write up a Monte Carlo simulation in Python. So the first thing we do is import the random library. And then we want to create a function that simulates an experiment, so essentially rolling the die until we get a 6. So we initialize our rolls to 0, and then we go through an infinite loop that stops once we get a 6, while incrementing our amount of rolls if random. So essentially, if our die roll is 6, we return rolls. And then if we want to run it an amount of times, and we can take the average. The total is our sum of the trials in range of n, and then we print the average. And when we run this, you see we're getting really close numbers to 6. And if we increase our n, we should get even closer numbers to 6. Yep, thank you.